Hello, it's Miss Portuese here. I thought it would be helpful to some students to go through the last test that you guys just took and just go through question by question to help you guys out. For the first one, right, chemical reactions are most likely to occur when reacting particles collide with the blank. Alright, collision theory is the idea of this. When particles collide, right, H2 collides with Cl2, we're going to make hydrochloric acid, HCl. We're going to make one HCl, two HCls. If the particles were not orientated the right way, like in this example here, if this collides with that, see how this atom and this atom are nowhere near each other? Right, this would be an ineffective collision. So maybe one HCl might be made, alright, but the reaction would not happen. So the answer is this: proper energy, proper orientation. For number 2, this first line here, right, potential energy is on the y-axis. This here is the potential energy of our reactants, what we're putting into our reaction. And we're here. For the reaction to happen, we need to get to this energy at the top. Alright, so the activation energy is the energy needed to get the reaction started. Right, so it's from the energy that we're at to the top. So it's this. This is activation energy. So the only one that matches up would be 1, going from the reactants to the top of the hill. Alright, catalysts. So catalyst speeds up a reaction. Remember with the elephant's toothpaste I showed you. I had hydrogen peroxide, I had the dish soap, nothing happened until I added a catalyst. Then we saw the foaming, right? We saw the color change happen. Alright, speeds up the reaction by providing a new reaction pathway that results in a different. So let's look at this. When we add the catalyst, let's say our new pathway looks like this. We're starting at the same PE, but now instead we're going to go here. Alright, we're lowering the hill. So now our new activation energy with the catalyst will look like this. Sometimes you'll see activation energy as EA, energy of activation. Alright, notice how when I added the catalyst, the activation energy changed, but what didn't change? The PE of the reactants did not change, and the PE of the products did not change either. So for question 3, we can cross off this. The heat of reaction, remember, it's not salt, it's pepper. Delta H equals PE products minus PE reactants. So the heat of reaction would be 3. It would be this, from the PE products, PE reactants. With the catalyst, that does not change, right? If both of these don't change, then the heat of reaction does not change either. So it's D. Alright, we just talked about how heat of reaction is pepper. This is my my PE reactants. This is my PEP. The difference between them is 2. So that's my answer. Alright, factors that affect reaction rate. There's a few of them. Increase temperature, increase pressure, right, decreasing the volume, same thing. Increase concentration. The more particles, the more likely they're able to hit into each other and have the reaction happen. Increase the surface area. So I showed you this in my demo with the dragon's breath. Remember, I had the candle and I sprayed that powder and you saw the poof, you saw how we saw a big flame, right? Because the increased surface area of the powdered substance. And then finally add a catalyst. That's how we speed up. Right. So we have the reaction. It says, at which temperature will the reaction occur at the greatest rate? We're looking for the highest temperature. So the answer is D. Number 6 has to do with number 5, right? Factors affecting the reaction rate. So we have iron, metal, placed in 100 milliliters of hydrochloric acid. Which change will result in the fastest rate of reaction? So increasing, right? Increasing surface area. So it's definitely not C or D. And increasing the concentration of HCl, right? See it here as well. Increasing concentration. So the answer is A. Alright, potential energy diagrams are our hills. So A and B are not it. Alright, it's either C or D. It's exothermic. Remember, exothermic means exits. So energy exits or is released. And this is going to be on the product side. So if we have like A plus B yields C plus, 10 kilojoules, right? Energy is on the right side. So we're going to go from high to low. In C, we're going from low to high. That's endothermic. In D, we're going from high to low. That's exothermic. Also remember, I told you guys, think about it. You're on a ride, right? What's the more exciting ride? This one, where you just go up and then a slight drop, or this one where you go up and then you have a big drop, and it's very fast and very exciting, right? Exciting, exothermic. Alright, table I shows us delta H's, right? Enthalpies, heats of reaction. If it's negative, that means that it's exothermic. Alright, so which indicates a net release of energy. That means exothermic. When you look at table I, you'll see that C is the only one that has a negative delta H value listed. Alright, we have another hill. These are our reactants. These are our products. Every interval represents 10 kilojoules per mole. What's the heat of the reaction? So remember, heat of reaction is our pepper. It's the difference between our plateaus or the flat regions in the graph. So every interval represents 10. Right, so this is 10 kilojoules per mole from here to here. This is 20, and this is 30 kilojoules per mole. So that's why 30 is my answer. Physical equilibrium is the same thing as phase equilibrium, where we have one compound and it just changes the phase back and forth at equilibrium. So A is our only answer where it's the same compound on both sides. And B and D are definitely not correct because there's no equilibrium arrow, right? That just means the forward reaction only. Forward equilibrium. So remember, I showed you guys equilibrium with the straw lab, where you had thought that you reached equilibrium when the volumes of both cylinder, like the black cylinder and the green cylinder, when the volumes were equal, you thought you reached equilibrium. That's not the case. You reached equilibrium when the volume stayed constant. Right, you kept transferring the water in the straws, and because you were transferring the same amount of water in both straws, right, since the rates were equal, your volume stayed constant. So, an easy way to remember equilibrium is this: REACE, or REACES, whatever you want to think. Rates are equal, and concentrations stay constant. Okay. So not this one, not this one. C looks promising. The rate is greater than the rate of the reverse. No, rates are equal at equilibrium, so it is C. And I gave you guys the example, right, with this: rates are equal, concentrations are constant. Imagine that your bank account stayed at about the same value, right? That would mean that the rate that you're earning is equal to the rate of your spending. So rates would be equal, and the concentrations would be constant, right? your amount that you earn each week would be the same that you spend each week, right? Those values would stay constant. Let's say it's Christmas or someone's birthday and you're spending a lot of money. Right now, the rate of spending is going to be greater than the rate of earning. So now you're not going to be at that equilibrium. If that helps. If you think about money and that helps you with the Reese. Number 12, solution equilibrium. We have BaSO4 makes, right? So this is the forward reaction. We have BaSO4. It can break down into Ba2 plus and SO4 2 minus. On the flip side, that SO4 2 minus and that Ba2 plus can combine in the reverse reaction to form BaSO4 solid. Right. So when we add more Na2SO4, meaning that we're increasing the concentration of SO4 2 minus, we are adding SO4 2 minus. Remember what I taught you? Another one. Add away and take towards. When you add SO4 2 minus, equilibrium shifts away and it will do this reverse reaction. Alright, so equilibrium shifts to the left, so it's not C or D. And what happens to Ba2 plus? So let's think about it. If the reverse reaction is happening and we are making, right, we're adding SO4 and we're making BaSO4 solid, we're going to be using up the Ba2 plus. Because think about it, right? We need this Ba2 plus to make BaSO4. So since we're making more of this BaSO4, we are going to use up the Ba2 plus, so the concentration will decrease. I explained this to you guys, if it helps, my little s'mores thing, right? If my product is s'mores, a way to think about this. Product is s'mores. And what goes into a s'more? Marshmallow, graham cracker, plus chocolate. If I found a whole big Costco box of graham crackers, right, and I increase my concentration of graham crackers, I can then make more s'mores. Right, equilibrium shifts to the left. I can make more s'mores. If I am making more s'mores, what am I using up? I'm using up my marshmallows. I'm using up my chocolate. Right, so if one of them increases on the same side, the other ones are going to decrease because we're making more of the other side. We're making more of the product, so we're using up our other reactants. For number 13, all right, disorder and energy. Systems in nature have a tendency to undergo changes towards. The analogy that a lot of chemistry teachers use is like a messy bedroom. So I'm sure that a lot of your guys' parents or guardians tell you, right, you gotta clean up your room. If it weren't for them telling you that, you would probably, I'm sure a lot of you guys would have food like all over your room. You'd have piles of clothes, right? I know that would happen. So think of the analogy. Systems in nature go towards low energy. Right? Think about it. You don't want to clean your room. Low energy and high entropy. And what does entropy mean? It means disorder. Alright, so systems in nature will go towards greater disorder and lower energy. 14 is another Reese, right? We're at equilibrium. We have this. What's happening with the concentrations? Concentrations stay constant. So, close reading, less than, greater than, no. Equal, no, that's the rates are equal. Concentrations are constant. For 15, so remember we learned that saturated means that it has dissolved the maximum amount of solute as possible. So if we have like a beaker and we have KNO3 aqueous, right, it means that we have this KNO3 dissolved in water. You guys probably think of it like this. I put salt in water, I mix it, it dissolves, done. That's not the case though. If it's saturated, we're at the maximum. it's going to keep on dissolving. So that solid that's in the solution, right, it's going to crystallize out, crystallization, it's going to crystallize out, it's going to get dissolved again. It crystallizes into a solid, it's dissolved again. This is happening at equilibrium when we have a saturated solution. So the rate of dissolving is equal to the rate of crystallization at equilibrium. Reese. Okay, Le Chatelier, right? This is a French scientist. Think of it. Le Chatelier is about shifting, right? When we add a stress to the system. So at equilibrium, everything is, right, rates are equal, concentrations are constant, but let's say that we add a reactant. Let's say that we increase temperature, we take away a product. We are causing a stress on the system, and the system has to shift one way or the other in order to balance it out. For 17, we have something plus something yields something plus something else. It's at equilibrium. The addition of a catalyst will. All right, let's think back to our potential energy diagrams. We have this. Let's say it's exothermic. We add a catalyst. What does that do? It lowers the hill, right? It lowers the activation energy. So let's say it looks like this. That catalyst is not a stress to equilibrium because it is affecting the forward reaction and the reverse reaction the same exact way. All right, so it's C. Part 2, short response. We have this reaction happening. State in terms of the concentration of SO3 what occurs when more O2 is added. So remember, guys, when it says state or explain in terms of, it means that whatever this word is, you have to have it in your answer. All right? When we add O2, remember, add away. We're adding O2 on the side. Equilibrium shifts away from it. The other way that I taught you in class is, remember, we did our teapot thing, where you put your hands up and it looks like this. Where your hands are up at the same level at equilibrium. If I add O2, O2 is on the left side, so that left hand is going to go up. Now your body shifts to the right. All right, so we added and it shifted to the right. So once again, if we're adding O2, we're going to make more SO3. More reactants yields more products. So the concentration of SO3 is going to increase. For this one, we have a graph. Concentration is on the y-axis, time is on the x. What can be concluded from the graph about the concentrations of the reactants and the concentrations of the products between time t1 and t2? Right, so we are dealing with this section of the graph. What do we notice about concentrations? It stays constant at 0.73. It stays constant at 0.27. Right, this flat line means it's staying at that same level. So we could say the concentrations are constant. Determine the change in the concentration of CO2 gas between times T0 and T1. So we are looking here. We're looking at CO2 from time 0 to time 1. So a lot of people got this wrong because when it says determine the change in, it is looking for a number value, especially since they give us the numbers. Right, so we have to use them. It goes from 1 to 0.73. So you can say negative 0.27 moles per liters, or you could say decreased by 0.27 moles per liters for that one. Alright, for this one, state how equilibrium shifts when the pressure is increased. When we are looking at pressure at equilibrium, we have to look at the number of moles. you look here. Our coefficient, that big number in front of a compound, is really a molar ratio. It tells us how many moles there are. So there's 2 moles on the left side. And remember, guys, if there's nothing here, that means that it's a 1. It's not a 0. If it was 0, we'd have nothing. 1 goes here. So we have 1 mole on the right. So what has more pressure, more moles? The left side. Right? So we add pressure, it shifts away. So equilibrium shifts right. Or you could say that equilibrium shifts to favor the forward reaction. Right? Because shifting right means that we are doing this forward reaction more frequently, right, to get it equal again. Alright, potential energy diagram, that is our hills. We have to look for, is it endothermic or exothermic? We see energy is on the left, right? Kilojoules is energy. If energy is a reactant that we're putting into our system, right, that means that it is endothermic because energy is entering the reaction. If it was like A plus B makes C plus 182 kilojoules, that would mean that energy is a product and it's released, and that would be exothermic. That's not the case. It's endothermic. So remember, if energy enters and we gain energy, we're going from low to high. So your picture is going to look like this. Lower energy to higher energy. Remember, exothermic would look like high to low. Last page. We have 2 equations, equations 1 and 2. State in terms of activation energy why the catalyst increases the rate of the forward reaction in equation 1. Remember, catalysts lower the activation energy. Number 24. Compare the rate of the forward reaction to the rate of the reverse at equilibrium. Reese. The rates are equal. That's it. State how equilibrium shifts when the temperature of the equilibrium system at equilibrium, represented by equation 1, is increased. Alright, so we're going to equation 1. We're focused here. Where is temperature? Right, temperature is like thermal energy. So the energy is on the left. If we increase temperature, right, we add temperature, it shifts away. So equilibrium shifts to the right. And I'm realizing that a lot of the ones were add away. But remember, if it said like decreased temperature, if it said temperature was lowered, we take it away, it shifts towards. Alright. Just so you have that clear. So for this one, since it's increased, it shifts to the right. Alright, so I hope that you found this helpful, and I will see you on Monday.